This is the continuation of a 5-part video series. This is part 3. We're still going to be talking about the disc and washer methods, but the difficulty level increases here a little bit. Sometimes we'll change the axes. Sometimes there'll be some little tricks here that we'll talk about. So this is a continuation of that. If you have not seen the first 2 parts of this video series, or you're not familiar with the disc washer method yet, the basics, I would highly suggest you go back, take a look at those. And here starts part 3. So in the last part 2, we talked about the washer method, and I prefer to call that the double disc method because it is a subtraction of volume. So what we're going to do here is just kind of fine-tune some of these techniques and get a little better here. So I've kind of pre-drawn the bounded region that we're dealing with here, and I've also pre-drawn these new axes of rotation. So now we're taking this bounded region here and we're rotating it around not the x-axis or the y-axis, but about the axis y equals 9. Okay, so there's some little adjustments here. So just to fine-tune some techniques here. First thing we're going to figure out is whether we need to use the disc method, whether this rotation is going to be a complete solid, or the double disc method. The books call it the washer method. And the way we do that is to decide whether there's going to be a hole in this, if this is going to be a subtraction of volume, or if it's just going to be a complete solid. So imagine this region being rotated around the line y equals 9. You can see that there's going to be this hole created here. It's going to look like a cylinder, but then there's going to be this bowl hollowed out of the side of this. So this is going to be double disc. So that's the first thing I'm going to have in mind. Second thing, imagine this being rotated, and say it to yourself right now, is this going to be a dx or a dy? So imagine that disc there and pinch it. Pinching that disc, it's rotating that way. This is going to be a dx. So I'm going to set this up as a double disc with the integrals in terms of x. So here we go. Pi r squared dx minus pi r squared dx. All right. So the radius always goes from the axis of rotation. There's going to be a big radius and a small radius. The big radius creates the solid. The small radius subtracts out a portion of that solid. So as we can see here, this big radius out to this outer boundary every time is a constant 9, because here's the axis of rotation, here's the outer boundary. So pi big radius is 9. The small radius is variable, and I'll draw some of these out. Here's a small radius, right? This is part of the hole. It's the radius of the hole, and here's the radius as well. Here's another radius. Notice this is not an x or a y value. It has to do with y. It has to do with the function value, but if I label this right here just some arbitrary point with the coordinates x, y, how do we get to that point? We start at the origin and move x this way and y this way. So here's actually the y value. Well, what's this? It's the difference of 9 and y. So right here is the difference of 9. I'm going to write 9 minus y as this small radius value. 9 minus y. But look, I cannot write 9 minus y here because this integral is in terms of x. So what is y? It says so right here. Y is x squared. And we've done this before. So y is x squared. So instead of y as this radius, I'm going to write 9 minus y. And so there's our integral setup. And if you're just starting out, I would recommend keeping it that way at first, but as you get more and more comfortable with it, go ahead and combine these two. And let's get the interval in there. We're going from the x values 0 to 3. And there's the setup. Notice there's a blank area right here for the shell method. That's in the video series part 4. That's the next video. So we'll probably start to compare and contrast these options here. Alright, look at the next one. We're taking this same bounded region. Here's our x-axis, here's our y-axis, here are the boundaries, x equals 3, y equals 0. This time we're going to rotate it around the axis y equals -2. So, which is right here. So again, we're going to set this up first. We're going to say, as we rotate this, imagine how that looks. Is this going to be a disk? Is it all complete solid? Or is it going to be double disk? Is there a hole taken out of that? And as picture that, you can picture there's going to be a hole taken out of the middle here. So this is going to be double disk. And picture those disks, pinch it. It's a horizontal pinch. It's a pinch in the x direction. So this is going to be another dx. Everything's in terms of x. So I'm going to set this up. Pi radius squared minus pi times the height of each of those, right? Don't forget that. It's not just magically in there. This is the width of each of those, or the height of each of those cylinders. So pi r squared times the height of that disk. Okay, and it's in terms of x, so we might as well set up the interval again from 0 to 3. And now let's talk about our radius in each one of these. So here's the axis of rotation. There's the large radius, the outer radius, and then there's the inner radius that creates a hole. So look at the radius that creates the solid. It varies. Well, how do we get there? Each time from here up to the function, aren't we taking 2, right? That's the axis of rotation, -2, and then the function value, right? Because if this is an xy point here, how do we get there? We go x in this direction, and right here is y. So just right here is y, and just right here is 2. So that radius is always going to be 2 plus the y value of the function. So that's the big radius. That creates a solid. And I'm going to write 2 plus, I can't write y. This integral is in terms of x. So what is y? Y is x squared. So 2 plus y. Okay, so there's our complete solid. Now we have to subtract the volume created with this hole here in this solid. So these disks that we're pulling out, adding them all up, have a constant radius of 2 each time, right? Because this would be the diameter here, and the hole would be created. I picture this as almost like a volcano that's on its side, if you want to picture it that way. So this is the constant radius 2. The integral is set up, and we're ready to move on to the next couple. Alright, so same bounded region in both of these examples. This one I changed it just so I can fit it to scale in the picture. It used to say it rotated around x equals -3. I changed it to x equals -1. So now we're going to picture this rotating around the line x equals -1, and picture if it's a solid or if there's a hole in the middle. It's either disk or double disk, and you can see that there's going to be this big gaping hole in the middle. So I'm going to set that up. And picture that disk, picture those disks, and pinch it. It's going to be a dy. Each of those disks has a small y value for the height. So let's set it up. Pi r squared dy minus pi r squared dy. Okay, so the outer radius is formed here, and the inner radius is formed here. Okay, so how do we do that now? Well, it looks like this outer radius from the axis of rotation to get to the outer part, it's going to be constant. Every time it's going to be 1 plus the x value of our no, it's going to be 1 plus 3. 1 plus 3. 1 plus 3. Or 4, 4, 4. So that outer radius is a constant 4. The inner radius is formed by taking 1 plus a variable amount. The other one was a constant amount. This one's a variable amount. So it's 1 plus this, and this is the x value. So again, if we just consider an arbitrary xy value, x is this distance, y is this distance. So here's our distance of 1, here's our distance of x. And we use x because, notice when we move up here, this radius is going to be 1 plus a different x value. It's always going to be the x value of our function. So I'm going to write in here 1 plus, look, I can't write x because everything, this integral is in terms of y. So what is x? X is the square root of y. So back down here, 1 plus x, because x is the square root of y. And the integral is almost set up. We have to get our interval in there, and because it's in terms of y, it's going from 0 to 9. All right, last one here for this part 3. Imagine this, and we're rotating it now around the line x equals 3. So picture it, rotate it. What do you think? Disk or double disk, also known as washer? Notice that this one does not have a hole in the middle, so it's going to be a single integral, pi r squared, and then pinch that disk. That's a y value, so this is going to be in terms of y. Pi r squared dy, and we'll go ahead and get the interval in here. Now we just have to talk about the radius. The radius of each one of these disks. Here's a disk. It's going to rotate here, right? Just so you can kind of see that. Here's another little, it's a smaller disk. Right? Here's another little one up here. Each of those disks, here's the radius of each one of those. Well, how do we describe it? If this is x, y, this is not x. X is the distance. How do we get there? From the origin, x, y is how we get there. So how do we talk about this? It looks like it's going to be this entire distance of 3 minus this x value. So right here is the distance x. This total distance here is 3. That's x. Our distance in here is 3 minus x. So that's our radius. 3 minus, again, can't put x here, so we're going to use what x is equal to. 3 minus x. And there's our integral. Again, what we're doing, it seems weird, it's maybe at this point seeming a little easier to you now, but that is finding the exact volume of this weird shaped solid. It almost looks like a volcano, but there's not a hole in the middle of this one. Alright, on to part 4. See you next time.